Okay, good afternoon, all of you. Let's get started. So yesterday we, started looking, or rather deriving the wave equations with a goal of realizing, an electrical kind of model wherein we can study how an ultrasound electronic system I mean, we need to develop an ultrasound electronic system. So towards that goal, we started studying, how the sound waves will be behaving while propagating in a medium. And we talked about longitudinal and latitude transverse sound waves, right? Or rather, depending on the medium, it can be a longitudinal wave or it can be a latitudinal wave, right? Or rather, transverse wave, not latitudinal. So then we from the first principles of Newton's laws, we started. What we said is, we are assuming a piece of the medium here, right? And one second, I'll just, yeah. So, and what we said is, if on x-axis is, I've shown the x-axis like this, and the velocity, the particle velocity of the medium at, let's say, a coordinate x, right, is ux, and the pressure is px, and similarly at x plus delta x, it is ux plus delta x and px plus delta x. Note the direction of the arrows, right, for the pressure gradient. This is important while we derive the equations and look at the sign magnitude, right? So we looked at that, and the area of this piece of fluid we assumed as A. So the total mass contained in this small piece of fluid is given by rho times A times delta x, right? Because our this is delta x, right? And area is the face of, let's say, this. This is the face of this cube. So the total volume is given by A times delta x, and multiplied by rho, we get mass, right? Then going to Newton's laws, the force is nothing but mass times acceleration, du dt. And du dt here, what we are doing is, we are saying the velocity component will have, it is a function of not only time but also x, right? And hence we kind of rearrange. I mean, du dt, we take the partial differential calculus and we rearrange and write it as del u del t plus del u del x multiplied by del x del t, right? And del x del t is again nothing but the velocity itself, which is u. So so this is nothing but Newton's from first principle, right? So nothing big here. Now, what is the force here that we are talking of? Is the pressure at this edge and the pressure at this edge. So the net force is what the difference between these two pressures, right? Which is px minus p of x plus delta x multiplied by A is the force that is acting on this piece of medium, right? So, and that equals this. So now as delta x tends to 0, I can bring this guy downstairs here like this, and as delta x tends to 0, I can write this whole thing as del p del x. And why is it minus? Because my x-axis is in this direction, and the gradient, the pressure gradient, is from here. I mean, is in the x direction. But when I'm writing the equation, the velocity is in this direction, right? So to take care of the pressure gradient, here I introduced minus del p del x, right? And even though we wrote del u del x for all practical purposes, we will say that the variation in velocity as a function of x is small. It is not significant, so we can approximate this to be small, and we can neglect this term for now. And So if I rearrange this, and this term, I can write del P del X plus rho times del U del T is equal to 0. So this is one important relation which we will use in the later slides. And also what we said is the density of the fluid through which the sound is propagating, the density of this fluid inside this cube is also a function of time. So the density has a DC component in electrical terms, meaning it has a time invariant component, which I'm writing as rho 0. This is constant, it does not vary with time, and it has a time varying component as well. For example, when the fluid, the sound wave is going through, is propagating through the fluid, right? Yesterday we saw how the fluid particles will move, which means that there will be changes in the density. However, it is also fair to say that the time varying component of the change of the density, the magnitude of that is much smaller to the absolute density, right? So this is one assumption. Okay, so now with this, if I put this guy in this equation here, I get del P del X plus rho naught del U del T equals 0. So this is what we are going to kind of carry forward from this slide. Okay, and also what we said yesterday, what is the mass that is changing in the volume that we assume? What is the mass that is kind of flowing out? So because it is flowing out, that's why we have written as minus. So minus A times delta X, so this is the volume, right? And del rho del T, right? So this is the mass that is changing inside the volume, and which we can also write the same change in this term. It is like this, right? Where at x plus delta x, this is the density and this is the velocity. So velocity multiplied by area actually will give me the volume. So if you look at the dimension, the velocity multiplied by area is going to give me the change in the volume, right? Multiplied by the change in the volume multiplied by the density at that point gives me the change in the mass at that point. So this is the mass that is flowing into the system or into the or rather I should say that this is the mass that is actually flowing out of this out of the cube that we drew, and this is the mass that is flowing in, rho x multiplied by ux, and these two I can equate, right? These two terms. And once I equate these two terms and again bring this del x downstairs here, then I can write this portion. I can simplify. I can take the limit as del x tends to 0, del rho u del x, and I can bring this term on this side and I can write this, right? So this is what we discussed yesterday also in the class. And again, replacing the rho here with rho 0 plus rho t, if I replace this guy here as well as here, right? If I rewrite, and also assuming that the time varying component of the density is much smaller, then this equation takes the form of rho naught del u del x plus del rho, the time varying component del t, this becomes equal to 0, right? Any questions up to this? So bear with me, and then so one convention that I have followed in the slides, anywhere I have not derived the equation or I am not discussing from where that equation is coming from, I've marked it in green because there are quite a few equations you will see in the slides which there's no point in going into the derivation of those because then it becomes too much physics and it's outside the scope of our subject. So if any one of you are interested in knowing from where this equation comes from, you can do some research and find out from where it comes from. But for now, anywhere I've used green color, I'm not going to discuss from where that equation came, and you have to trust me that this relation holds true. Okay, so this is one relation: rho T by rho 0 equals K times P. P is the pressure, right? So in a fluid, the time varying component, the density that varies with time, right? The the fractional change in density with time can be equated to the pressure that we are applying on the fluid, and K is the compressibility constant. It kind of makes sense, right? You can see why this equation makes sense, right? If the pressure is high, then, and of course if the pressure is fluctuating with time, right? If it keeps changing with time, then we will get the time varying component will be proportional to the pressure that we are applying, right? So now, and compressibility, just like Young's modulus and the elastic, the compliance coefficient, they were inverse of each other. Here for a fluid, the K is the compressibility constant, and that is inversely proportional to the bulk modulus, right? K is equal to 1 by B. It's just very simple, this thing. Again, I'm not deriving this, and this is unimportant for in the scope of the present discussion. So now if I replace this relation here, then I will get an equation like this. And again, simplifying this, we actually had this. If you we had this relation we had from our previous slide. If you go back, if we go back here, so this was the relation we had, right? Del P del X plus rho naught del U del T is equal to 0. So this was one equation we had. And this is the second equation we got from the mass change in volume. So the first equation we got from what? First equation we got from simple from using Newton's law, right? And the second equation we are getting by equating the mass change in volume with the pressure and the density change in the fluid, right? So this is the second equation. The first equation, of course, we had derived already earlier, this guy. So now if I replace, if I use both these equations, right? If I use both these equations and put, let's say, this equation here or this equation here, whichever way, and that you can do, and you will land up with actually two relations. I am showing you only one relation here, but you are free to look at, just like the constitutive coefficients in piezoelectric, right, where we can go from one domain to other. Similarly, here you can probably put this equation here or this equation here, and you will get two such relations. So if you do that, we land up with a very nice, small, concise relation which relates the velocity with time and x. So this is one relation that we get, and if we solve this equation, what we find is the velocity of the particle as a function of x is nothing but a sine wave, and that can be denoted by, it has few variables. One, of course, is the amplitude. Ux caps is the amplitude. It has a time varying component, which means it is characterized by a wavelength or a frequency. Here we are talking of WL. CL is the speed of the wave in the medium. X, of course, is the axis that we have defined. Time is T, right? So basically all, these two above equations, we chose, or rather we dealt with two equations. One was with Newton's law, and then the second was this mass change in volume, and utilizing both those two equations. So this guy came from the mass change in law, and this guy came from our Newton's equation. Combining these two, we land up with a relation which shows how the velocity u is changing with respect to time as well as the axis, the location, I mean on the x-axis, how does the velocity change, right? So we'll end up with a nice sine wave kind of a term. Now what is what? CL, what is CL? So from this equation, CL is nothing but square root of 1 by k times rho naught. And again, k, we have discussed what is k, rho naught of course we know. And because it's 1 by k, I mean this is, the bulk modulus, just inverse of that, right? So this is this, that is CL. And which means, I mean, I can rewrite this equation in another form. Instead of writing it like this, I can write it ux sine omega lt minus kx. So k is nothing but the wave number. So this k is nothing but the wave number. We call it the wave number. And that is nothing but 2 pi divided by the wavelength. So wave number actually denotes the wavelength. And that is also equals the omega L by CL, right? So this relation again is pretty well known from from normal wave equations, which you studied in physics in class 11, 12. You would have seen this relation, right? But the point is the same relations hold true when the sound is propagating in a medium. So please note, I am denoting these quantities as omega L and CL. L stands for the longitudinal wave. For transverse wave also, we can come up with similar relation, but I mean we are not discussing transverse wave separately. But for longitudinal waves, this is what leads to so three things we will take away from the previous two slides. Point number one, we used, so the first thing is we used Newton's law. Second, we used conservation of mass, right? So from these two basic principles, we derived ux, which is a function of time and x here, and of course it also depends on the characteristics of the material properties, the fluid properties, right? And that you can see CL, the speed of the wave, is dependent on the density as well as the bulk modulus, and the wave number of course is given by omega L by CL is equal to 2 pi by the wavelength. So far so good, right? Any questions up to this point?
Sir, in the previous slide, you took the approximation that del U by del X is equals to 0.
Yes.
So in this,
Yes.
in the current slide, we also have this one term del U by del X in the equation. So why?
Here, right? Here, right? Here, right? That's what you're saying, right? This guy, right?
So why isn't it taken to be 0 over here? Like,
So it is. So it's about. So that's a good question actually. So yeah, let's go back to the previous. So if you see here, we are multiplying it with 1 by k, whereas in the previous thing, right, I had assumed both the complete term ux with del u del x. This complete term, I'm saying that this is a very small quantity. When you multiply, see the speed of the particle itself is low, and that as a function of x, this complete term itself we are neglecting, because we have this, see the speed of the particle is itself not, these are small numbers, right? When it's going in a fluid, right, the particle movements are small. So u multiplied by del u del x itself is very small, whereas there, if you see, we have this 1 by k term comes. Not only that, right? You can say that, sir, you said that del u del x, I mean x does not, or the velocity is not a strong function of x, but finally the term that we are deriving, we are seeing that this is there is a dependence on x, right? But the point that we have to note is del u del x is not zero. It's u multiplied by del u del x. The complete term is zero. I mean, approximately, it's very small compared to the other term. If you look at the previous term, it's very small compared to that, and that's a fair approximation to make. And I actually referred for this equation, right? This equation I myself was not very convinced, but I referred multiple, material, and this is the best kind of explanation that people are given. In fact, much of these derivations are not even done with, in such detail in most textbook or material, but you can think about it, and I think it is fair to say that the velocity itself is a small quantity, and multiplied by this itself multiplied by the function, the gradient of u as a function of x, that we can assume to be zero. And with that, we'll end up with, so actually what happens, right, when we are studying or when we are deriving these equations, right, we see nothing is perfect. If you kind of put these equations in a real world scenario, you will see that there may not be an exact match. And then we will do some curve fitting. We will say, okay, these non-idealities are there, and based on that, we'll do some adjustment in the equations. But as a first order of understanding, the key concept here is that yes, the velocity does have a sinusoidal kind of a property, which is a fair assumption to make, and it varies with time. It also has, it is also dependent on x, right? Along with the fluid properties that impacts the wavelength or the speed or the frequency, right? The fluid properties itself decides the characteristics of the wave flowing through the medium. So that's the message that we will take from here, right? And anyway, as I said, you don't have to mug up, big time all these equations, but I would expect that, if somebody were to ask you or derive that, you may probably go through these equations and show how this. So this is the the small equation that we derive. And in fact, not only u, so the thing that I'm not deriving here, can you tell me what I'm not showing here? I've not, so just like u as a function of x, right? What have I done? I've used these two guys to come up with an expression for u, the velocity. I could have done the same for pressure, right? So that is the thing that I'm not showing. So using these two equations, you can replace u also and put it in this equation, or and then you will come up with a similar expression with, of course, some difference will be there, which will relate pressure as a function of time and a function of x. So that I'm not showing here as such. If you're interested, you can do that. Now, again, there are two equations which we are not going to look into the derivation. You have to kind of trust me that, yeah, these two relations are correct. So the pressure, the absolute pressure P, is also related to the displacement. Phi is the displacement, the particle displacement, and this is the bulk modulus, right? So this is related, the pressure is related to the displacement by this expression, and these two, again, you have to pardon me, I'm not going to derive this. And so if we use these two expressions, if we use these two expressions, we'll end up with an expression which will relate the pressure with the particle displacement. Here again, you see that there is this fluid property that comes into picture, and x is, of course, the x-axis that is there, right? So now u, of course, we know, which is the velocity, is del phi del t, right? So which means del u del t is del 2 del phi by del t square, right? So this equation we had from the previous, the first slide, we had this equation from Newton's law. This equation we had, right? And this, we came up with this here, right? So this is the same stuff. Now, from these two relations, what I can do, so this is del 2 phi del t square, and this is del phi del x square, right? I come up, so this guy is there, this guy is sitting here. So I replace del u del t, I know, is del 2 phi del t square, right? 1 by, so I'm just using this, this equation we had, this we had from here, and I'm just using this basic relation between u and phi to come up with this equation. You can do the math and see it works out. This actually, yeah, you can do it if you want. So we will remember, so out of the whole last 3 slides, right, we'll take away this. Why do we take away this? Because this relates displacement of the particle as a function of x. The previous equation that we saw related the velocity of the particle as a function of x and time. The other equation which I have not derived, which I have left it for you to see what happens, is how the pressure in the fluid that changes with time, or x, that I have not derived. Okay. So the key takeaway from all of this is, again, in general, the speed of wave in general in any material is given by square root of the elastic modulus divided by the density. Now, if it is gas, what we see, and in gas or in liquids, the waves will propagate. I mean, we will have longitudinal waves. It will propagate in a way, it will show longitudinal behavior. Or in other words, the particle will be moving parallel to the propagation of the wave. The direction of the particle movement will be same as the direction of the wave propagation. Whereas for transverse waves, we know that it is the particle movement will be perpendicular to the direction of the waves, right? So the speed of the waves for different, we can express this in different ways. So this is for gas. It's the gamma is the specific heat ratio, P is the pressure, rho is, again, not even in textbooks you will see in instrumentation textbooks. We need not go into the actual derivation of this. We'll take it from the physics guys, and we'll trust that they have done a right job. And these equations will just kind of, what it tells us is the velocity is inversely proportional to density, or it is proportional to the elastic modulus, like B here, right, or Young's modulus here, right, or Poisson's ratios here. So as long as we understand the basic relation, we are good. Okay. So now that we know that the particle displacement or the velocity shows a sinusoidal behavior, what we will do is now try to derive the acoustic impedance of the fluid, and the acoustic impedance of the fluid, and that makes a lot of sense if you see, even though I'm not showing the derivation, but here if you see, the acoustic impedance is given by pressure divided by the velocity. This makes a lot of sense, right? Because when we talk of current flowing, right? So this resist. So let's say this is V. The voltage is, of course, across the resistor is V. We know V is equal to I times R, which means R is nothing but V divided by I, right? So V is nothing but the potential difference. So we are equating the potential with pressure. So the pressure difference across the the face of the small mass that we took, right, of the fluid, right, the pressure difference across that divided by the velocity. Velocity is, again, you can equate it to the current flowing. So this ratio is going to characterize the acoustic impedance of the material, right? So again, we had this relation from Newton's law. So now if I replace ZA is given by P by U, right? So in this equation, which we got from the Newton's law, we are replacing U from this equation. U is nothing but P by ZA, right? I've just put this guy here. I land up with this. And now I'm getting pressure as a function of X. I'm getting it like this. And the same thing we could have got from the previous pair of equations, which I said I have left it to you. But the point is, so this we had already derived from the previous slide, which I said that I'm not showing, but it is exactly same as the velocity equation, right? So we had Px as a function of omega L and X. So this was the function Px, right? So ZA, so if I put Px here, right, then I will land up with an expression for ZA, the acoustic impedance, which is again a function of the fluid property, square root of B times rho naught, or it can be also written as CL times rho naught. CL is the speed of the wave in the fluid. So the acoustic impedance is also, so acoustic, see the pressure and the velocity of the wave, right, is not under our control. I mean, velocity is of course, but the pressure that we are exerting, right? Pressure, you can say, is not a fundamental material property. So ZA, but we are using this relation to come up with an equation to relate the acoustic impedance of the fluid with a fundamental property of the fluid itself, which is, let's say, the bulk modulus, the density, right? So this is what ZA is. We'll take this understanding that, okay, the acoustic impedance offered by the fluid is again a characteristics of the fluid given by this. Now, what is intensity? And the reason, again, you will see all of these coming into picture in the subsequent slides, how ZA is coming into picture, or, you know, I mean, the acoustic impedance or how the reflection will happen, the transmission will happen. We'll see in the subsequent slides. So bear with me. So the intensity or the power density, intensity and power density we can use interchangeably, is nothing but power by area, that we know, right? The amount of power that you are applying, you know, with let's say you are applying a power, or let's say on a certain area. So power is nothing but work, right? So let's say when we say light intensity, what does it mean? So that means, you know, the brightness of the light falling on a certain you know, area of the wall, or, you know, a sphere or whatever, right? So that power divided by area. So power is nothing but work, as we know, which again is force by distance. And I mean, sorry, I have multiplied power with time. I've multiplied time both on the numerator and denominator. I'm replacing power with work, and area with area multiplied by time is the same thing. And work is nothing but force into distance, right? So just by rearranging, so force divided by area, this guy becomes pressure, and distance by time, this guy becomes velocity, right? So essentially the intensity can also be defined as the pressure, as the product of the pressure and the velocity, right? So which means pressure and velocity, right? So which means, so ZA, we know ZA, so this is intensity. Again, going to, if you look at the power, right, dissipated in a resistor, that is what V square by R. So here you can relate to something very similar, right? The pressure square of that divided by the acoustic impedance, or P into U. This looks very similar to what? Voltage and current, right? U is synonymous to current and pressure is synonymous to voltage, right? And this again, U square RA, this is again nothing but I square R, where U is synonymous to current and R and ZA is same as, you know, the impedance that is offered, right? So this is the power, this is the power density that is associated with a wave propagating in a medium. The medium has a characteristics acoustic impedance given by ZA. The velocity is a sinusoidal function which varies with x and time. Pressure is also actually a sinusoidal function which varies with x and time. So the power is given by the velocity of the propagation velocity multiplied by the acoustic impedance. Also, what we see is the intensity as the wave propagates, right? The intensity does not remain constant. So for example, let's say the wave is propagating from x equal to 0. And if we were to plot omega x, right, we will see the intensity will keep falling with the distance that the wave has propagated. Again, that makes sense, right? When we talk, so let's say when I'm talking, probably someone sitting next to me will hear my voice loud and clear, but someone a little bit far will hear it a little bit fainter, and somebody a little bit farther will probably not be able to even hear me, right? So the intensity is also a function of time. X, the axis that we had defined. As the wave is propagating, the intensity keeps falling with distance x. And this alpha w, we will note this is actually a power attenuation coefficient, alpha w, right? So now if we write or if we draw what happens when a wave, sound wave, is incident on, so these are two materials. So this is, let's say, or two fluids. This is fluid 1 and this is probably fluid 2. So when the it can be fluid or it can be an object, it can be anything. It can be this, the fluid 1 can be a liquid, fluid 2 can be actually a solid also, right? So what we see is the incident wave, a portion of it will be reflected. Theta I and theta R, we know the relation, and some portion of it will be transmitted. So the fluid 1 is characterized by speed of propagation of the sound wave, which is again a characteristic property of the material. And how is C1 defined for different fluids or different material? Is this, right? This equation. So depending on the fluid, depending on the bulk elastic modulus, depending on the pressure or depending on the density, we can define the characteristic speed of the wave propagating in the medium, right? So these are two separate fluids having two separate characteristics. Some portion of the wave is going to be transmitted and some portion is going to be, so this is reflected and this is transmitted. Some portion, so it's not like the full thing is transmitted or full thing is reflected, right? So the reflection coefficient is defined how, so alpha W, which is again the power attenuation coefficient. When we are talking of power attenuation coefficient, we are talking of the wave propagating in the same medium. It's not that the wave is going from one medium to another, right? The wave is going, let's say, passing through air with, as a function of x, the intensity is going to fall as we measure the distance of the measurement area from the source. So this is attenuation coefficient, the power attenuation coefficient of the wave flowing in the same medium, right? What is reflection coefficient? That is given by the intensity of the wave that is reflected divided by the intensity of the wave that is incident on it, right? It's pretty straightforward. Similarly, the transmission coefficient is given by the energy that is transmitted into the next medium and the energy or the intensity that is incident on the medium, right? So WR by WI is alpha R, WT by WI is alpha T, right? And so this is one fundamental equation that is there. So if you see here, so sine theta I divided by, I think I had a derivation for this. 1 second, please. Probably not. So probably not. So this I think should be, yeah. So again, I think you have to trust me here that the sine, so this equation sine theta I by sine theta t, sine theta I by sine theta t will have a relation, meaning the angle of incidence and the angle of transmission is related to the fluid velocity C1 and C2 in this relation, with this relation. And alpha R is actually given by, I'm kind of a little bit lost here. I thought I had, just hold on guys. I think, just hold on. Yeah, so I will be actually discussing the derivation of those equations in the subsequent foils. So that's what I think, but to make the, yeah, we'll come to those equations, we'll come back to this, but for now, yeah. So for now, so alpha R, so we are going to see how this is going to be derived. I'm going to discuss this. So here I'm just kind of showing that if a wave is propagating from one medium to the other medium, so these are the relations that will be true, right? And this again is pretty straightforward. The total energy of the incident wave can be equated with the energy of the wave that is reflected and the energy of the wave that is transmitted, right? So this is one relation, and alpha R plus alpha T is equal to 1. This can be again easily derived. Alpha R plus alpha T, if we do here, right, is WR plus WT divided by WI, right? And we know WR plus WT is equal to WI. So this means this is equal to 1. So that's the reason why alpha R plus alpha T must be 1. So if somebody tells you that, okay, the reflection coefficient of the wave going from one medium to another, if alpha R is given, we should be able to calculate alpha T. Not a big deal, right? And what is alpha R? This relation we are going to derive in the subsequent foils. And sine theta 1, and again this one also we are going to derive. So this is like a summary page which should tell you, I mean, if you are revisiting the lecture, right, this is like a summary page which will tell you that once the wave, and this is where the electronics will come into picture later on, once the wave is incident, some portion of the wave is going to be reflected and some portion is going to be transmitted. And what is the relation between the reflected wave and the transmitted wave? We have quite a few, stuffs relating them. One is that this, right, the transmission coefficients alpha R and alpha T. Then these angles theta I and theta R, they are related by the speed of the waves that are propagating from medium 1 to medium 2. We are going to look at that. So this is like a summary this thing, right? So let's proceed and see. So because we know that we derived that the displacement is a function of x and time, and we saw it was like a sine wave kind of a thing, right? So then the moment we talk of sine waves, we can relate that in the complex plane, right? So phi xt can be written, can be represented in this form as a complex wave, right? So it is like a more generic way of representing the sine wave with in a complex form, right? So the phase, of course, so this portion is phase. Please note the phase is dependent on k and omega, right, which are fundamental properties. From here, anyway, so this equation we had earlier, or actually even from here we can see delta 2 phi delta t square is minus omega square phi, right? So now with these two things in place, let us look at, we are going to derive those sine theta 1, sine theta 2 equations, right? So let us see how those equations come, all right? I mean, so let's say we have this reference medium where our sound wave is propagating, and this is another medium 1. So the reference medium has a density rho and c, and the second medium has rho 1 and c1, right? So the pressure that is incident, the pressure. So when you are talking of pressure, right, we don't talk of direction as such, right? We say that the pressure will be normal to the surface that we have shown, right? That's what we mean in any case, right? So the pressure that is incident is in this direction. The pressure that is coming from the medium 1 is again normal to the surface, and the pressure because of the reflected wave is also in this direction. The reflection is happening in the surface, like this, but the pressure, when we are talking of the pressure because of the incident wave, the pressure is applied because of the incident wave in a normal direction. Similarly, the pressure that is a result of the reflected wave, that also will be normal in direction, and that has got nothing to do with the theta that is associated with it, right? So while the pressure is shown as normal, but if you see the velocity, when we are going to talk of velocity, we are going to talk of the velocity as a reference to the direction of the incident wave and the reflected wave. So U1, so if you see, there is a fundamental difference. The way I have shown the pressure components, which I have shown as straight lines, whereas the velocity is shown parallel or in the same direction of because these are longitudinal waves, right? So the velocity, if the wave propagation direction is this, the velocity of the particle is also shown in the same direction, right? So now what we are doing here, so this is our the displacement equation. Phi x as a function of it's a complex in the complex form we have represented it like this, right? So now if I were to, because the wave is incident in this direction, right? If I and look at my x-axis here, my x-axis is in this direction, right? So the equations that I derived in the previous page, what was x there? X was actually in the direction of the propagation, right? So the x that we derived in the previous slides was actually in the direction of the propagation. The cube that you drew, right, was in the direction of the wave propagation, right? In this slide, however, when we are talking of reflection, we are talking of x. The direction is taken such that the interface is shown wherever so let's say the two mediums are interfacing horizontally, right? So this is my x-axis. So this x-axis and the equation, the x-axis that was there, which we related to the pressure or the velocity equation, that x-axis was with respect to this, right? So now if we actually kind of rearrange the equation and take my new x-axis, then the pressure equation that we have derived can be written as this. So x instead of x, right? So this is z, this is x. So this component, I'm not writing omega t here because omega t is nothing but is a function of time. All what I'm right now interested in seeing how the pressure is changing in my space, in my coordinate system here. So if I change the x-axis that we had assumed there, if we change the coordinate system and rename the x-axis in this direction and the z-axis in this direction, then the same equation can be written as this, right? Pi is equal to P0 E times e to the power I of whatever, blah, blah, blah. This is the, the complex form of the equation. It's nothing but the same x coordinate has been replaced in a new reference frame, okay? This equation we had discussed earlier. Of course, we didn't derive this, which means, so if I del phi del t, if I do del phi del t, if I put it here, I get phi I. What do I get phi I as? So phi I is minus of I times P0 Any questions on this? I'll probably take another. Tomorrow I'm going to revisit this portion. We are probably going to stop here today because I think I want you to take this point why the x-axis has been changed. So first of all, I want you to understand that because we are dealing with sine waves, we are talking of the displacement as vectors in the complex plane, right? Once we take it to the and there are advantages of taking talking in the complex plane when we talk of vectors, right? We can do a lot of simple algebra we can do, right? So I want you guys to take this today with you, and tomorrow again we will revisit. We'll start from this portion and probably see where we land up with. Okay. Okay. Thank you, guys.